sklearncovarianceOAS. Description: explain in detail the OAS outlier adaptive shrinkage method. A technique within scikit-learn's covariance estimation is designed to handle datasets containing outliers. Traditional covariance estimation methods are sensitive to outliers, which can lead to inaccurate estimates. OAS addresses this by shrinking the covariance matrix towards a more robust estimate. This shrinkage reduces the influence of outliers on the final covariance matrix. Inputs. Input 1. Explain in detail data matrix X, a numerical dataset represented as a NumPy array or pandas. Data frame. Each row represents an observation data point, and each column represents a feature. Input 2. Explain in detail optional parameters. OAS allows for customization through various parameters. These include: assume centered, a boolean indicating whether the data is centered, mean subtracted. If true, the computation assumes the data has zero mean. Shrinkage, the shrinkage parameter that controls the degree of shrinkage towards the robust estimate. Support fraction, a float between 0 and 1. Determining the fraction of data points considered for robust estimation. Contamination, the proportion of outliers expected in the data. Outputs. Output 1. Explain in detail covariance matrix C, a square matrix representing the estimated covariance between features. The matrix dimensions are equal to the number of features in the input data. Output 2. Explain in detail optional outputs depending on the specific implementation. OAS might provide additional outputs. Precision, the inverse of the covariance matrix. Shrinkage, the effective shrinkage parameter used during estimation. Steps. Step 1. Explain in detail robust estimation. The OAS method first performs a robust estimation of the covariance matrix. This involves identifying and downweighing outliers in the data. Common techniques for robust estimation include minimum covariance determinant (MCD) or other robust estimators. Step 2. Explain in detail shrinkage. Once a robust estimate is obtained, OAS applies a shrinkage process. The final covariance matrix is a weighted average of the robust estimate and a simpler, more stable estimate, often the identity matrix. The shrinkage parameter controls the balance between these two estimates. Metrics. Metric 1. Explain in detail robustness. The performance of OAS can be measured by its robustness to outliers. One approach is to evaluate how well the estimated covariance matrix is affected by the presence of different levels of outliers in the data. Metric 2. Explain in detail accuracy. The accuracy of the covariance matrix estimation can be assessed by comparing it to the true covariance matrix if available, or by examining its performance in subsequent applications, such as in machine learning models. Visualization plots. Visualization plot 1. Explain in detail scatter plots with ellipses. The estimated covariance matrix can be visualized using scatter plots of pairs of features. Ellipses centered on the mean of each feature pair can be plotted with radii determined by the estimated covariance, providing a visual representation of the data's correlation structure. Visualization plot 2. Explain in detail heat maps. Heat maps can depict the covariance matrix, showing the correlation between different features through color gradients. This allows for easy identification of strong correlations and potential multicollinearity. Fine-tune parameters. Parameter 1. Explain in detail shrinkage controls the degree of shrinkage towards the robust estimate. A higher value leads to greater shrinkage, reducing the influence of outliers. Experimentation is often needed to find the optimal value for the specific dataset. Parameter 2. Explain in detail support fraction defines the fraction of data points used for robust Estimation. Adjusting this parameter affects the number of outliers considered during the robust estimation. Step. Uncertainty methods. Uncertainty method 1. Explain in detail. Bootstrap resampling. This method involves repeatedly sampling with replacement from the original data and estimating the covariance matrix for each sample. The variability in these estimates provides insights into the uncertainty of the estimated covariance. Uncertainty method 2. Explain in detail. Bayesian methods. Bayesian methods can be used to incorporate prior information about the covariance matrix and derive a posterior distribution, capturing the uncertainty associated with the estimated covariance. Challenges and fixes. Challenge 1. Explain in detail sensitivity to outlier proportion. If the actual proportion of outliers in the data deviates significantly from the contamination parameter, the estimation process might be affected. Sample use case that resulted in challenge 1. A dataset with a higher outlier proportion than assumed might lead to insufficient shrinkage, resulting in a less robust covariance estimate. Fixes to challenge 1. Adjust the contamination parameter. Experiment with different values to find a better match for the actual outlier proportion in the data. Use robust outlier detection methods. Employ more sophisticated outlier detection techniques to accurately identify and handle outliers, improving the robustness of the estimation process. Challenge 2. Explain in detail computational complexity. The robust estimation step in OAS can be computationally intensive, especially for large datasets with many features. Sample use case that resulted in challenge 2. Datasets with millions of observations and hundreds of features might experience significant computational overhead during the robust estimation phase. Fixes to challenge 2. Subsampling. Use random subsampling techniques to reduce the size of the data used for robust estimation without sacrificing significant accuracy. Approximate algorithms. Consider using approximate algorithms for robust estimation, such as those based on randomized techniques, which can trade some accuracy for significant speed gains.